Right, thank you very much. I'm very excited to talk about my research today. So the title is Using a Magic Wand to Break the iPhone's Last Security Barrier. You can see this is the magic wand I used. Actually, if you try to Google magic wand, the first 20 results is not what you expect, so it took me quite some effort to find this one. Let's get started. So, my target device is the iPhone 4, which has the A4 CPU. It was released in June 2010, and if you're wondering, hey, why are you talking about like such an old device? This research actually dates back to 2019, where this was the latest device with a bootrom vulnerability, which was limerain, so this is pre-checkmate. Yeah, and gives you the highest possible privileges, which we will need. It has no dedicated security coprocessor. It has a hardware AES engine, and it has hardware-fused keys. And the engine also allows you running encryptions and decryption with AES with your own keys. This is not necessarily required, but you kind of want to have this if you're targeting an unknown implementation. So you do need Oracle access to encryption. It gives you Oracle access to encrypting and decrypting AES in CBC mode. Motivation. Well, you can extract the model-specific GID key. This is shared across all iPhone 4s. That allows you decrypting the firmware without actually having the physical device on you. It doesn't really have any benefits for devices with the bootrom exploits, but assuming you do that on a newer device once through glitching, and you get code execution, then you extract the key, then you can always decrypt the firmware, so maybe useful for other targets. There is the device-specific UID key, which allows, if you extract that allows scalable offline cracking of passcodes. And the passcode key decrypts the user data. But to spoiler, this whole attack that I'm presenting here only benefits the effort, attack benefits only outweigh the effort for passcode, which are more complex than 8-digit numeric. If your passcode is less complex than 8-digit numeric, you might as well just crack it on device because you do need the same primitives to get started. So the requirements for the EM attack are, well, code execution on the target. You want to have Oracle access to the AES engine with the target key, obviously. You also want to have Oracle access with the known key. This is technically not required, but you really want to have this if you're targeting an unknown implementation. You want to have a low latency trigger for your oscilloscope measurements. And, well, you need an EM probe, you need an oscilloscope, you need computational resources, and so on. So let's take a look at the target setup, software side. I do use the limerain bootrom exploit to gain early code execution. I boot a patch state 1 bootloader, which does low-level initialization like DRAM, for example. I boot a patch second stage bootloader for just a more convenient environment to work with because iBoot actually has a custom shell, so if you do a little patching, you can run your own payload there, bare metal, but still with some functionality already available like printf, UART, and stuff like that. It doesn't have a proprietary USB interface, and it has UART. You have full access to RAM and MMIO, and it's kind of the best noise-free environment you can get because there's only one CPU per active, it has a cooperative scheduler, and it usually has no unexpected interrupts. On the hardware side, well, I'm using the USB and the UART, so in order to get UART on these old 30-pin connector devices, you need to build the UART cable like this. Basically, this is just a breakout board, you solder in the USB wires, you solder in a resistor, and you solder in UART, that's pretty much it. Using like an FT23A board, you get UART to USB, so if you have two USB connectors, one for actual USB, one for UART. Well, how about triggering our scope measurements with the UART? Well, no. UART stands for Universal Asynchronous Receiver and Transmitter, and the asynchronous is a bit problem because it's also possibly buffered on sender and receiver side, and it's definitely not real-time. Furthermore, if you use a standard bitrate of 11,200 bits per second, which is 8.68 picoseconds per bit, 1 byte takes about 95 microseconds. Anyways, so if you send immediate start-stop signal, which is like 190 microseconds, assuming there's no buffering in between, which there is, it's too slow. Our AES is long done by that, so that's way too slow. But there are peripherals on the phone. Well, ARM peripherals are connected over GPIO. So what peripherals are there? Well, there's buttons, there's modules like Wi-Fi, Bluetooth, GPS, gyro, compass, control signals, LCD, camera, but most importantly, there's buttons, which are connected to GPIO. So what exactly is GPIO? GPIO is general purpose input-output. And those pins are configured at boot, actually, by the system. So since we have code execution, we can reconfigure those GPIO pins, right? So if we reconfigure the volume buttons, we can actually use them as an output instead of an input. So GPIO is memory mapped I/O, so we write to this address in RAM to set the pin high or low, and bam, we have a perfect trigger for our measurements. This is much faster than UART, and it is synchronous. How does that look like in practice? Well, you can just disassemble the board, just take out these volume buttons, just solder wires directly to them, and then write to the address in RAM, and then you get like the high signal and low signal. Easy. This is the payload I used. So basically, the iBoot already has a function which you can call, which runs AES on the hardware engine. And I put this hook in there, so at some point it jumps to that code, and then that takes over. Basically, the important thing here is that I have one assembly instruction, which is one store byte instruction, which sets the trigger high. The next assembly instruction starts the actual AES. Then I have a little loop, which checks if the AES is done. And then I have yet another assembly instructions, which sets the trigger low. So this is as good as it gets, basically. And by that, we can have like high pin, the AES, and low pin, and we already know where to look in between for the AES. Measurement setup, well, running AES in a loop uses more power than USB provides, which discharges the battery, and you have a limited measuring time, which kind of sucks. So just remove the battery and use a custom lab power supply, and solve the problem. Easy. Obligatory slide for the equipment I used. I'm not really side channel guy, so I just went up to the university. It was like, hey, give me your best equipment, and this is what I got. I guess the important part here is the 40 gigasamples per second sampling rate, which I believe I really needed. Other than that, it's just a slide for you looking up later. By the way, I will release these slides after the talk. So for the analysis, what do you do first? Well, you gather information. You search online, manual reverse engineering of the bootloader. Luckily for that device, a lot of public work has been done already. So from that, we know we have a AES engine which supports AES 128, 192, and 256-bit AES. We have the UID key, the GID key, and we can supply custom user keys. We can use it in CBC mode and in ECD mode. Okay, so far so good. Let's do some more basic analysis, timing analysis. We have the start and the end GPIO signal. We can just study the traces, and we can run multiple blocks of AES. So instead of one block, we'll encrypt like 8 blocks or something like that. Okay, I done that. So basically, we get something like this. In the top left, we have 2 blocks encrypting, then 4, 8, and 16. So what do we see? We have something at the beginning and something at the end, which kind of looks constant. And then in the middle, something which seems to grow the more blocks we encrypt. So, okay, so this is probably where some of the encryption is happening, right? So the blue line is the GPIO trigger signal, and the red line is actually the EM signal. It gets even more clear if you plot them on top of each other. So at the beginning, you see the constant parts, which are probably not interesting for us. And then the variable parts is where we expect to see some AES. So from doing this timing analysis, one block of AES. So if you take the trigger start to stop, the GPIO is like 3000 nanoseconds. If you go to these peaks, the lower green line, which I deem to be the interesting peaks, and the AES should be somewhere in between, we have 755 nanoseconds between each. If you, instead of one block, encrypt 16 blocks, and then do like the longer measurement and divide by 16, you get for the GPIO 205 nanoseconds, and for the peaks 120 for 25 nanoseconds. So we know, okay, one AES is probably faster than 124 nanoseconds. So we already can get some very basic information. After that, we can do some actual side channel analysis, which is first we do leakage assessment. So I use the non-specific t-test, basically which you feed the AES either random inputs or a fixed input, and you collect thousands of traces. So for the fixed input, you have also the same intermediate values in the internal AES state. So for non-masked implementations. And we expect to have the same power consumption. So if the groups are distinguishable just by the EM traces, then an attack might be possible. If that doesn't succeed, we can try other things like higher order t-tests, and there's lots of fun math and statistics which I have no idea about, but I know it exists. So what is the t-test? In case you never heard of it, t-test is a statistical hypothesis test which confirms or rejects a hypothesis with a certain likelihood. So the hypothesis that we have is the null hypothesis, which assumes that two sets are drawn from the same distribution rather than two separate distributions. I have images to visualize that in the next. Basically, the t-test gives you a statistical value for determining the likelihood that two given sets are drawn from two distinct distributions. So what does that mean? Assume you have set A and set B. In the top two pictures, we have a fixed and a random from a fixed set and from a random. So these are actually two different sets, which gives us a high absolute t-value. And in the lower two ones, we draw them from the same distribution, which you can see also by the colors, and that will give us a value close to 0. So if the value is high, we think it's two different sets, and we can potentially distinguish that. By collecting 10 million traces, we can see we have a very nice t-value. So usually the threshold is, if it's above 4.5, then we have some kind of leakage, and we assume, okay, we have leakage. And here the value is much, much larger. Although the very large peaks are probably not the interesting ones, because actually, when we talk to the AES engine, we transfer data to the AES engine, and then we transfer the data back. And these are very loud and leaky, and we're not actually interested in this. So I think these are the AO transfers, which in turn means the AES is probably in between. So let's zoom a bit in. But even if we zoom in, the values are huge. You can see they go up to 200, and we only want them to be higher than 4.5 or lower than minus 4.5. So something is leaking. If we also plot them, the t-value on top of the EM traces, which we deemed the interesting peaks, we can see, okay, so even in the interesting part, we have good t-values. Okay, good. Something is leaking. Let's move on to the next step. So the next thing I did is I used the signal-to-noise ratio. So what is that? Well, signal-to-noise ratio uses a power model to sort traces into different groups based on a model value, right? An accurate power model of the inner state of the S will have distinct groups, like distinct sorting, and other power models will have random groups. So the SNR does two things. First, it gets a value on how different are these groups from each other. And it gives you info about the accuracy of the power model, which you can use for an attack. So the other thing is, since we're not doing this at one point in time, but on many points in time, we also get the info on when in time the model fits very well. So we also get like timing information. So explaining the signal-to-noise ratio, basically here as an example, you sort these rigs, I call them, by model, and then compute SNR how good the groups are sorted, judging by edges. So for example, in the top ones, we sort them by edges, and we can see, okay, this is a very good sorting, so the SNR value is 0.92. And in the lower, we sort them by color, and you can see the colors don't actually quite match the groups, so we have like a lower value. So high value means it's distinct, so we want to see high value. Right. So as a model, I use next the input and the output, or the Hamming weight of the input plaintext, of one input plaintext byte. I vary that and try that for different bytes, and also the output of what we get out, and the Hamming weight of that I use as the model. So we have 9 groups in total. And then we can check where the signal is seen. So if you repeat that for several bytes, here I do encryption of 8 blocks of AES, and let's take input byte 5, then the Hamming weight, and use this as a model for all of the 8 blocks. We can see, okay, we have a good signal here, and then using the output bytes, doing the same, and we have different signals there. Other bytes yield similar values. And this is also interesting to see that from that we can learn that the input seems to be, or probably is transferred at once, while the output is first we get 4 blocks, and then 2, and then again 2. So this is already interesting to see. If we overlap that with our EM signal, this kind of confirms the hypothesis that loud peaks are the AO transfer, because this is exactly where we see leaking of the output, right? So this is like not the interesting thing. It's like IO transfer, not the AS itself. But we also know that in this time span, definitely at least 4 encryptions happen, because we see the input leaking, and then we see the output leaking. So we know somewhere in between has the AS to take place, right? So great, this is more information. Now I actually want to go a step back. Where do you put your probe, right? Because this already, I put the probe somewhere, obviously, but where should you actually put the probe? Well, I had like a lecture at university, which tells me, so you take the probe, you move it around, you look at the EM traces, and try to identify the signal. Find just a spot with the strongest signal. Easy enough, right? Well, the reality is much different. There is no visible signal whatsoever. There is lots of jitters. Staring too much at traces makes you go crazy. It's like if you stare for them for like 6 months, you'll find the ghosts of the past, the present, and the future Christmas. So don't overinterpret random noise peaks or whatever. I'll show you what I mean. This is like 500 traces put on top of each other, already filtered, already aligned. You don't see anything in there, but there is 5 AES taking place. We'll come back to a similar image like that, and you'll see what I mean. But for now, just assume, like, even if you think, oh yeah, that at the back is AES, no, that's not it. You cannot see the AES in here. Well, best strategy is you just put it somewhere and hope it's good. What else are you gonna do? So what you want to do then is you want to search for a leaking power model. Because sure, the Hamming weight of the input or the output works fine, but it doesn't really help you. You want to model AES intermediate state. And then if you do that and you find an accurate model, you can actually use that for an attack. I tested all of these models for various implementations, like literally everything I could think of. I had a different course describing different hardware implementations, so that came in handy. T-table implementation, round-based implementation, register after certain steps, after each steps, after one round. Tried many models for different bytes, for different rounds, for encryption, for decryption, like value, Hamming weight, zero value, all of that. It took forever to compute that. And the worst part is you don't know which model is the correct one and how many traces you need to actually get something leaking. So I eventually gave up on that because SNR has actually some problems for practical attack. SNR divides traces into groups, and resources are always tight, especially RAM or VRAM. I was using a custom OpenCL implementation, so I was doing that on GPUs to speed it up even more. I processed more than 50 million traces with 80,000 points per trace. And yeah, more groups require more computing resources. So if I take like 8-bit Hamming weight, I get 9 groups. That's okay-ish. But if I try larger models, 128-bit Hamming weight, I get too many groups, and this is not efficient to actually compute anymore. So I had to try something else, which got me to the CPA, which is correlation power analysis, different statistical tool. Basically, it works. You use a power model to create a modeled power trace based on a value. And then CPA tells you how similar your hypothetical model is to the real trace. And it has a much lower footprint than SNR because you have just one single model trace rather than X groups of real traces. So CPA explained, imagine you have the real trace on the left, and you have model A, which is, and model B. And then you can see that model A, the horse, is much better correlating than the giraffe on the right. So this is what we use for hacking the iPhone. Anyways, so I tested several models with CPA. With CPA, I could actually test 128-bit models, so I could basically do the Hamming weight of the full state. Because the full 128-bit register might be updated every round, who knows? And if so, larger models will actually leak better. So I tested lots of things again for every round, and eventually I was lucky, and I found the leaking model. So this is the model that I found, and I guess quick side note, I was targeting a decryption, but I will explain the model on encryption. So I was actually giving it some data and asked her, hey, decrypt this, and this is what I was measuring, but I will, for the sake of simplicity, this model is modeled on encryption. So the leaking model is the Hamming distance between one state and the next state, like the full 128-bit distance. So if we were to attack the first round of encryption, or which I actually did is the last round of decryption, you take in the plaintext, you XOR the key, and then you XOR that with the plaintext, with the key, through the S box, through the permutation layer. And from that, you take the 128-bit Hamming weight, and this is what I used as a model, and that actually worked. By doing so, I could distinguish, and we can see one peak in each round distinguishes significantly. And this actually gives us even more information about this black box hardware implementations that we didn't know anything about, right? So we know one round takes 5 nanoseconds. Well, just take the distance between the two peaks. 14 round of AES takes 70 nanoseconds. To process a full block of AES, you need 95 nanoseconds, including post and pre-processing, whatever that is, which I basically took by measuring round 1 of block 1, the distance to block round 1 of block 2. So from here we can say, okay, let's assume one round is computed in each clock cycle, which I do for the sake of simplicity. Not that it really matters, but that would tell us that we have an AES which is clocked at 200 megahertz. Okay, nice. And yeah, we can even distinguish like full blocks. Here I plotted the leakage of each round in the same block and in the same color. And then you can see, you can also clearly distinguish the AES blocks. And remember the earlier picture where I said you can see the ghost of the Christmas? So if you put it on top, this is actually where the AES actually is. And if you see, okay, what signal do I actually see from the trace? You don't see anything. It's not like you can see peaks or anything, but there's just nothing. So, yeah, but knowing, like, from that picture, we can actually see, so, okay, if I see that on my computer, I just look for that peak in the scope and then I know, okay, a little bit earlier and a little bit later there is a block of AES, which is clearly, like, we estimate the locations of these based on the peak that we have. Next, well, remember I said I put the probe just randomly by educated guessing, right? Which doesn't really yield any good results. But now that we have a leaking model, we can actually do a full chip scan. So I divided the chip in a grid of 24 times 24 squares, recorded traces on each position, do the correlation, which does require the working model. This is why I couldn't do it earlier. And then we find the optimal spot for the attack. Although I did run a few problems, well, very few traces can actually be recorded. My major limitation was disk space. Okay, I said, okay, I want the chip scan to not contain more than 6 terabytes of compressed traces. By the way, this is about 80% compression rate, which means I only could record 150,000 traces with 40,000 points each and only 4 blocks of AES. In contrast, what I was doing before is 100 million traces with 8,000 points and 8 blocks of it. So take these results with a grain of salt, because it's only vague orientation. So this is not too reliable, but for me it was good enough. I could make this heat map of the actual how good it correlates. So we have 2 spots which seem really nice. Just randomly pick the one I marked in green, which results to this exact position of the probe. And this is what I used for my attack. Because remember, so far we were working with a known custom supplied key, but we actually want to, like, the full goal is to get the unknown key, right? Also, at this point we're working with the 128-bit Hamming weight, which is not really practical for attack, because that would require you guessing a full state of AES. So we actually need to test smaller models, which I did, and luckily it worked. It leaks less, but it still works. So the 100, test 8 Hamming weight 8-core model, record the decryption, and then attack the last round of decryption. Here model with the encryption. This is the model that I use for the actual attack. So basically, I give the engine something, it decrypts it. I need that decryption, and on that decrypted value, I can run the attack. For the actual attack, I record 8 blocks of AES, 256 CBC decryption with random ciphertext. I record 500 million traces, which took me about a week. So transferring everything to UART is kind of slow, so instead I would transfer, by the way, I used UART for communication because the scope was a Windows machine and getting UART to work was easier than the proprietary USB protocol, and it had other advantages. But basically, I sent over a seed, which would then, using a pseudo-random number generator, generate a batch of ciphertext on the device, which it would run through the AES engine where I could record the traces. And because I have the seed and the same PRNG, I could recreate those on the PC without having them to transfer. Although, because I need for the attack the actual decrypted values, the processed values. In the second step, I needed to send them over all again, and then have the device actually decrypt them, and then store them to use them for the attack. Which then I used USB, which is faster than UART, but still decrypting everything also took me a week. And then running the actual correlation on my custom GPU implementation also took me a week. So this is about like 3 weeks for the full attack. Okay, so known key correlation. We tested with a known key with the 8-bit Hamming weight. We estimate the leaking point in time for the correct key byte and compare that with wrong key bytes. Right, so this is like over time with the correct key byte. And if we take that point in time and instead do other key bytes and correlate over other keys, you can see target key is clearly visible, so we do get a good correlation, and we can successfully recover the key. So the big question is, how many traces are actually needed for an attack? Because I said, okay, 10 million traces, 100 million traces, 500 million traces. The truth is, it varies a lot. If you get lucky, then you can recover some key bytes with as little as 30 million traces. So you can see this is like extremely good leakage. If you're not so lucky, some bytes will need 300 million traces to be recovered. Here are 2 more examples, and you can see, okay, the top one we got lucky again, we don't need a lot, and the bottom one we need like 300 million again to get that reliably. Although, there are other strategies than just recording more traces, because well, storage is a problem eventually. Like, even if you have a large NAS, like one of that recordings takes me like 6 terabytes, and for testing, I had to do multiple recordings, then delete some, and then try again, and so on. So storage is a big issue. Well, what else you can do is you can check nearby points in time. Basically, if you look at this, and then I go forward a time, so you can see it's likely this one and not the one which was highest first, right? So if the one like a time step before and after is also very good leaking, then it's likely that one rather than like a random noise which is there in one frame but is gone in the other frame. Well, the other obvious thing to do is, well, remember I was using 8 blocks of CBC. Well, you can just use a different block, right? So if one key byte on a specific block isn't leaking very well, you have still the traces, and just target that key byte on a different encryption block, and that might work better. And since I recorded 8 blocks anyway, this was a viable strategy. And actually the one that we see before here, which is very noisy, on the different block, that key byte actually had very good leakage. Was easily extractable. So, now the fun part, do we actually get the key? No. But you can get the hash. So if you get the key and hash it, this is what you get. So this is the SHA of the actual key. What can we do with the extracted GID key? Well, we can decrypt firmware without the actual device. I tested that by downloading the firmware and decrypting the key back, which is keys encrypted by the GID key. And compare that to what is written on the iPhone wiki, and we can see, okay, that's the same result I get with my OpenSSL script. And yeah, so we can see it works. Well, what else can we do? We can recover the UID key. I actually wrote a custom implementation to cracking the user passcode on the on GPUs. Now that we have the UID key, we can do that. But I suck at GPU programming, So instead of taking my implementation, actually a friend over at Hashcat implemented that. So you can use Hashcat to crack iPhone pins, well, given you have extracted the UID before. And we can see a 12-digit numeric passcode according to the Apple white paper, where we assume that one attempt takes 80 milliseconds. That would take 2,536 years. While if you take 3 weeks to extract the UID key and then throw in 8 Vega 64 GPUs, you can get that as fast as 23 days. So, yeah. Well, that was it. Now it's time for some questions.
Thanks, Tihmstar. So, do we have... Yes, we have, of course. Just 1 second. Coming to you.
Thank you for your presentations. I have actually questions. The first question is that you try the power leakage. Is quite successful on the end. I'm not sure how you do it.
So actually a colleague tried that, a PhD student at my university tried that. The problem was that I could do good alignment on the EM traces, while on the power traces you couldn't realign them. So you had to run the attack on unaligned traces, which again are very jittery. And because of that, you needed to use roughly the same amount of traces. So it's possible with both EM and power traces, but due to the alignment problem, the power isn't better than the EM.
Thanks. And another question should be as so I'm not familiar with the actual ES implementations on this chip. Is that not protected?
It's a black box. Nobody knows. It's not something that's documented. None of this is documented. You can reverse engineer the bootloader to figure out how to talk to the hardware, but no idea how it's actually implemented. So from the side channel, I built a model, which I think is how it works, but no idea if it actually works like that.
Thanks.
Thank you. Any other questions from the audience? Yes.
Thank you for the presentation. I have a question suggestion. Have you tried to use another statistical distinguisher rather than correlation? For instance, linear regression analysis, where you could, consider that the leaking model is not Hamming weight, but it's something where the bits leak kind of differently each others, and then perhaps decrease the number of total traces you need to recover the key?
No, for 2 reasons. A, I have actually no clue about how these statistical things work. And B, this was a project for my master's thesis, and I had a limited time. Once I got the leaking model, I just used that. So it's not like I had unlimited time with the university lab equipment where I could just do what I want. If I had still access, I'd probably try to do the newer phones, but I don't have access.
Thank you.
Thanks. And the last question? Anyone? No. Okay, then a round of applause to Tihmstar. Thanks.